This is lecture 9 or week 9 of Psych 1040, and we have several topics to cover in this particular lecture. We're going to be talking about this new comparison distribution, the distribution of means. We'll be talking about the Z test. We'll be talking about issues about power and errors in hypothesis testing. Remember that what we've been saying in the past few weeks is that the entire group of individuals or instances about whom we hope to learn, usually in our theory testing, is the population. And because we often can't afford to measure the entire population, we usually work with samples. We draw a sample, which is a subset of the population for closer study. And one way that we can draw a sample is to give each set of n number of elements an equal chance of selection, and this is called then a simple random sample. If a sample is truly random, if it really meant that every single member of the population could have been picked at chance, then we can use this frequency distribution to tell us the probability of any sample statistic. So we can take the frequency distribution of the population to give us estimates about what the chances are that we'll get individual X values. So you did that a lot last week when we were talking about what proportion under the curve above a certain Z score, for example, would exist. And just even talking about specific X values, whether or not they're rare or they're more frequent and so on. But you can also do this with things like means. So you can use that frequency distribution to tell you about the probability of getting a particular mean, or standard deviations, or other statistics, for instance, correlation coefficients that are called Pearson R. So that's what's really kind of great about picking samples at random from populations, is that then you can use that characteristic about the population to help you figure out the probability of some sample characteristic. So that means that given a certain mean or a standard deviation or whatever, we'll go ahead and draw a conclusion about characteristics of the population. It will be most accurate, however, if the sample was randomly selected and it's representative of the population. Now, last week, what we learned about was hypothesis testing about a single X. So you remember we had the example of the air traffic controller, Joe, and we compared his score to a normal distribution to see whether his score was significantly different from the rest of the population. This week, you're going to learn about how to do a hypothesis test about a sample that's drawn from a population. So this is not a single N. This is a sample that has several people in it. And you might think that because we're going to be using a sample and we're looking at the mean of the sample, that if we're going to compare means, then why not directly compare our sample's mean to the mean of the population of individual scores? That is, if I just got done telling you that we can look at a population and figure out what the probability is of getting any particular mean from a sample, then the reason you might think then that would be the comparison distribution, but it turns out we don't actually use the population of individual scores. And the reason we don't do that is that with any particular sample, we're unlikely to get the population mean by chance anyway. And this last point is especially true if we have a small sample size. So, in fact, using small sample sizes mean that we're not going to get an accurate estimation of the population mean. For example, imagine we have this population of people's pulses, their pulse scores. And so these are a whole bunch of individuals. And we're going to go ahead and draw people randomly from this population to create a sample. So we randomly choose person number 1. And person 1 has a pulse of 73, which actually is the mean of the population. The mean of the population is 73. And then we pick person number 2, and he or she has a pulse of 68. So now if you take these two people's scores, we would have a mean of that sample that would be lower than the population mean. We go ahead and grab person number 3. This person has a pulse of 72. So if you take these 3 pulses and put them together as a mean of a sample, you would see that they would have something less than the population mean. Person number 4, let's say we grab at random, has a pulse of 80, so that would bring it back up again. And person number 5 has a pulse of 85. Now, if that's my sample, I have these 5 individuals with those 5 different pulse rates, and I say, okay, well, what's the mean of that sample? It turns out that it's 75.6. It's not 73. So it's not, even though these 5 people came from the population that's got a mean of 73, I'm unlikely to just get a sample that had that population mean to begin with. So what we need to do then is visualize a different kind of distribution. And we're going to call this new distribution a distribution of means that have samples of 5. So what I would do is just grab from the original population 5 people, 73, 68, 72, 80, and 85, find out that their mean is 75.6, then throw them back in and grab another 5 people, 74, 65, 74, 83, 90, find out that they have a mean of 77.2. Randomly choose another 5 people. They give me a mean of 71.6. And then another 5 people, and they give me a mean of 71.6 as well, but they have different scores. And I would keep doing this over and over again. So we continue for many, many samples of 5 each, just grabbing 5 people at a time from the overall population and figuring out what their mean is. So now what you can see so far is I've got a table here of 21 different samples that I've drawn and what their respective means were. And I could keep doing this on and on and on, hundreds and thousands of times. In fact, theoretically, I could do this an infinite number of times, right? So I could just keep doing this for a long, long time, just grabbing samples of 5 and figuring out their means are. And then let's say what I do is I go ahead and draw a histogram of all of these means. So I'm going to take all of those means that you just see there, and plus all the hundreds more, and start to say, okay, how often do I get a mean of 71.6 or 74.5 or whatever? So here's the histogram, and you can see this histogram is trying to plot some of these sample means that I got. Now, they're not all evenly occurring in like a nice bell-shaped curve. There's some dips here and there. But you can see that among all of these different means, the most common mean that I'm getting is 73. And in fact, the mean of this histogram is 73. So this resulting distribution that I just created is special, and it has a special name. It's called a sampling distribution of the mean. Now, sampling distributions of the mean in the textbook are also called distributions of the mean or a distribution of the mean. And so sampling distribution means just another fancy way of calling the same thing. Sampling distributions of the mean, in case you missed it here, are created by taking a very large number of samples, all of the same sample size n. So I'm going to try to approach infinity with this. Keep grabbing samples of the same sample size, doing it over and over and over again, taking their means, and then making a plot of all of those means. Keeping in mind that for any given distribution of means then, the n is always constant. I'm always using the same sample size as I draw this very large number of samples. Got that? Just to kind of help you visualize this, many years ago when I first taught statistics, I asked my students in my class to actually create sampling distributions of the mean. And what they did is I gave them little slips of paper in a box, and I said, okay, all the little slips of paper in there are the population. And what I want you to go ahead and do now is draw out 3 slips of paper, 3 different numbers that are in there, and figure out what their mean is, and then take the 3 slips of paper and put them back in again. And I said, do that a couple hundred times. So they sat there for like an hour, drawing out 3 slips of a paper from the box, figuring out the mean of the 3 numbers, and putting the numbers back in the box, and doing that over and over again, taking all of these little slips of paper 3 at a time, finding out their means and putting them back in. And then after they'd done it a couple hundred times, I said, go ahead and make a histogram of what all of the means look like. And therefore, they had their sample distribution of the mean, their sampling distribution of the mean. Again, theoretically, you would do it an infinite number of times. We didn't have that much time that night, so I only had them do it a couple hundred times. But you get the point, and believe me, it was very difficult for them to do this. It was boring to sit there and over again keep drawing different sample size, the same sample size, but drawing another sample and another sample of 3, just to go ahead and prove my point. Now, it turns out that if you, instead of using 5 as your sample size, or 3, and you used a bigger sample size, the samples that you would get, the sampling distribution of the mean that you would get, would become more normal. So the shape of it doesn't necessarily look like a normal curve when you're using a small sample size. But if you use a large sample size, like an n of 10, your resulting sampling distribution of the mean will look more like a normal curve. And this is what's known as the central limit theorem. The central limit theorem states that even when the original population of raw scores isn't a normal distribution, if you go ahead and create a sampling distribution of the mean with a big enough sample size, your resulting sampling distribution of the mean will start to look more like a normal curve. Now again, it's not that I'm going ahead and drawing out 200 different samples or 500 samples or 1,000 samples. It's the sample size that I'm talking about. Like it's having 200 samples where the n is 10, or 200 samples where the n is 25, or 200 samples where the n is 50. As I increase the sample size in each of those three examples, the resulting sampling distribution of the mean, or the distribution of means, looks more and more like a normal curve. In fact, some special properties then of distributions of means. First of all, it turns out that the mean of the distribution of means that you create is equal to the mean of the population of individual scores. So if you take that histogram that you get from all those different means and look at the mean of the histogram, you'll find that it equals the mean of the population of individual scores. Slight detour. Our best guess as to the mean of the distribution of the means, and therefore the mean of the population, is our sample mean, because that's what we're normally working with. It's just one sample. We have a sample mean. So think about it. Are we more likely to get a bigger estimate, a better estimate of the population mean if our sample size is bigger? Well, it turns out yes. The bigger our sample mean, the more likely it is that we're going to correctly estimate the population mean. So with small sample sizes, the mean of our sample is probably more influenced by extreme scores, but as the sample size increases, this is less likely to happen, and we're going to have a better estimate then of what the distribution of the mean is, or the population mean is. A second property of a distribution of means is that the variance, the spread of the distribution of means is equal to the variance of the population scores divided by the sample size. So if I know what the original population's variance is, and then I divide by the sample size that I use to create this distribution of the means, I will now have the variance of the distribution of the means. Another little detour here. Keep in mind that with a small sample size, we're going to get more variability, a bigger spread in the distribution of means due to extreme scores and outliers. So again, when we're working with smaller samples, we get a lot more variability because the samples are going to include strange scores, outliers, and so on every once in a while that will kind of throw everything off. So the more individuals in each sample, the less spread out the distribution of means is going to be for those samples. Okay, so the more individuals in each sample, the less spread out the distribution of means of those samples. So it turns out we can actually compute the variance of the distribution of the means, or the standard deviation of the distribution of the means. And you can see I have it here as the formula that comes out of the book, that if I want to figure out what the variance of the distribution of means is, it's got this little variance symbol with an m. That's equal to the population variance divided by n. So if I know the population variance, I divide by n, I've got the variance of the distribution of means. If I want to know what the standard deviation is of the distribution of means, I just have to take the square root of that number. So take, just like I've done before, where I had the variance and took the square root of it, I get the standard deviation. You can see in the calculations below there that I'm now going ahead and figuring out what the standard deviation of the distribution of means is. All right, away from that detour, let's go back again to the properties of a distribution of means. The third property is that the resulting shape of the distribution of means is normal if, first of all, the original population of scores was normal, or even if it isn't originally normal, the sample size was large enough, say over 30. Okay, so there's two ways that the resulting shape of a distribution of means is going to take on the shape of a normal curve. One is if the original populations of scores had a normal shaped distribution. So remember, an example of that would be a lot of biological variables or even IQ. They have original population scores that will take on the shape of a normal curve. And so if you go ahead and create a distribution of the means for some sample size, like let's say 20, and you go ahead and just do an infinite number of samples with the n of 20 and plot all of those means, the resulting distribution of the means you'll get will take on the shape of a normal curve. But the second point here says, even if it isn't originally normal, that is the original population did not have a normal curve, the sample size, if it's large enough, will give you a resulting distribution of means that looks like a normal curve. And usually this has to be over 30. So if you use an n greater than 30, you'll usually end up with a sampling distribution of the mean, or a distribution of means that takes on a normal curve, regardless of what the original population of scores look like. Okay, these properties of a distribution of means are all important because that now allows us to create a new kind of hypothesis test where we can look at the means. And the specific one that we're going to be looking at today is when you know the population standard deviation or the population variance. So this is when you're looking at means and you want to know if your mean of your sample is significantly different based on some null hypothesis, but you actually do know the population standard deviation. It's been given to you somehow. Maybe it's because it's a standardized test that's been given to many, many people before. This kind of test that we're going to do is called a one-sample Z-test. Okay, a one-sample Z-test. And we can go ahead and just take those 5 steps of hypothesis testing that we introduced at the last lecture. So here's a variation of those same 5 steps. First of all, we're going to make some statements about the population parameters. We're going to determine the population parameters, assuming the null hypothesis is true, basically looking at our comparison distribution. We're going to determine a cutoff point. We're going to determine the probability of our sample statistic, assuming the null hypothesis is true. And then if it exceeds that cutoff point, we'll reject the null hypothesis. And if it doesn't, we're going to retain it. So let's go ahead and try to work that out. Let's go ahead and conduct a Z-test using the distribution of means as our comparison distribution. So here's our example. Kirsty and 2 other teachers are teaching a total of 5th grade students at Oakwood Elementary, a primary school in the United States. So she's got these 100 students in grade 5. And after the students are given an IQ test, she finds that they have a mean of 110. So these 100 5th grade students at Oakwood have a sample mean of 110. Now, as I mentioned before, IQ tests are usually set up to have a mean of about 100 and a standard deviation of 15. So here are our known values. The population mean is 100 and the standard deviation is 15. So Kirsty and these other two teachers want to know if their students at Oakwood are somehow different from what you would normally expect on an IQ test. So the question is, are Kirsty's students significantly different from what you would expect by average? So let's go through this on hypothesis testing and set up our statement about our parameters. So we're basically setting up our null and our alternative hypothesis. Our research alternative hypothesis, the one that Kirsty would like to show, is that the students at Oakwood come from a population where mu is not 100. Okay, so that's where they'd like to think that this is what's going on here. They think that there's something different about their students, that they don't have a mean of 100 in their population. But the null hypothesis, the one that they need to reject before they can go ahead and go for their alternative hypothesis there, is to test whether or not they actually come from a normal population where mu is equal to 100. So now we need to think about what our comparison distribution is. And as I said, because we're working with a sample, and a sample that has 100 in it, we're going to have to talk about a distribution of means as our comparison distribution. So in this case, we're going to work with a distribution of means where we have samples of 100 students each. So we want to kind of imagine this distribution of means where we took out 100 students at random from the population, figure out what their mean is, put them back. Do that again, pull out 100 students, figure out their mean, and put them back. And do that over and over again, like an infinite number of times. And then look at what the mean would be of that distribution of means and what its standard deviation would be like. And as I just showed you in some previous slides, we can figure out what the population standard deviation is here, or what the distribution of means standard deviation is here, given the formula that I have listed on this slide. So to find the standard deviation for the distribution of means, what we want to do is take this formula where you take the variance, which is the variance squared there is a symbol with the squared sign over n, or to reduce that down, everything that's under the radical, we could just say, take the population standard deviation and divide it by the square root of n. In this example, the population standard deviation is 15. So if they come from a population that is normal, doesn't have anything unusual about them, they would have a population standard deviation of 15. So we take that 15, put that in the numerator, and we're going to divide by the square root of 100. That's the sample size that we have here. So here it's 100. So that would be 15 over 10, or 1.5. So that means that our spread of the distribution of means for an n of 100 is 1.5. The mu is 100. So this sampling distribution of the means, this comparison distribution, if the null hypothesis is true, would have a mu of 100, and its spread would be a standard deviation of 1.5. Now in step 3, we want to determine what the cutoff is going to be. So again, I'm assuming that this thing's going to look like a normal curve because it's IQ. And this is a bidirectional hypothesis, so we need to determine the z-scores that represent this critical region where we would reject. Let's assume the usual 5% significance level in this example. If you go and look in the book for the Z table, A1, we're going to find that a z-score of 1.96 is the point where 0.025 of the scores are in the tail beyond that. So where those two arrows are in this picture, that would mark off plus 1.96 and minus 1.96. So those are z-scores, plus 1.96 and minus 1.96. And it turns out that if our sample statistic exceeds one of those 2 points, then we're going to go ahead and reject the HO. But you notice that I've come up with z-scores as the cutoff, and I don't have a z-score yet. All I've got is a population mean, or a mean for the distribution of the means, and a standard deviation for the distribution of the means. But you'll see that that's not that hard then to convert to a z-score. That is, let's go ahead and take our sample mean, that's 110, plug it into this formula. So I'm going to take 110 as our sample mean, subtract it from the population mean, or the mean of the sampling distribution of the mean when the HO is true, and divide by the standard deviation for this distribution of the means. That's 1.5, this thing that we calculated just a moment ago. So if I take 110, subtract 100 from it, and divide by 1.5, that gives me then a z-score of 6.67. That means I've translated Kirsty's sample, their mean of 110, into a z-score, given everything that was available here in this problem. And that would mean then that her sample mean would be 6.67 standard deviations above the mean in this distribution of the mean. So you can already tell that's pretty extreme. So we need to determine the z-score, again, assuming that this null hypothesis is true, and then compare the results of steps 3 and 4 to determine whether to reject or retain our HO. And as I've drawn here, you can see that our obtained z of 6.67 is way past a positive z-score of 1.96. So our z, 6.67, is far greater than the upper cutoff score. So that means the chance of getting a z value of 6.67 is extremely rare when the null hypothesis is true. This definitely happens less than 5% of the time. So we're going to reject the HO. We're going to reject the null hypothesis. And what we can conclude then is that Kirsty's class has a significantly higher mean IQ score, comma, Z is equal to 6.67, comma, P less than 0.05. So we know now that, yes, her students are significantly different, and they probably come from a population that has a higher mean than the one that was originally depicted by the null hypothesis. So that is the same sort of logic we went through last week. All we've done now is we're working with a sample mean, and we have to therefore use for a comparison distribution the distribution of means. And so you just have to take these characteristics that we've introduced in this lecture and put them in to help you figure out the problem for a distribution of means. So of course, you're going to want to work out some more examples of this in the text, and hopefully you can do that before you take the quiz so that you can feel like you know how to do a Z test. Now, on a slightly different topic, I want to ask this question. What about any errors that we could make just by chance? That is, it's possible that I told you that you could have a sample mean like Kirsty's that could happen when the null hypothesis is true. It would be extremely rare, but it could happen. And by rejecting the null hypothesis, we could be making a mistake. That is, there might not be anything special about these people. It just turned out by chance that they had a mean that was much higher than what you would expect by the null hypothesis. That kind of decision-making and recognizing there could be an error in our decision is why we never like to say anything so definitive in our conclusions. We don't like to say we prove something because we could possibly be wrong. And so we have a way of kind of formalizing the way that we make these errors in hypothesis testing. So what you can see in this little table is I have in the top there, I said, let's say you're the researcher and you've done your statistical test and you've either concluded to reject the HO or retain it. Okay, so you've got these two columns, one for reject, one for retain. And let's just say that in reality, that's what's down on the left there, the reality is that you should have rejected it or you should have retained it. So it's saying that, yeah, if we could really know what the truth was about the nature here of this population, we would know whether or not we really should have rejected it or really should have retained it. Now, if we concluded that we rejected it, to reject the HO, and reality is, yeah, this person, this sample, whatever, really comes from a different population specified in their hypothesis test, that would be good. That'd be a correct decision, right? Because we'd be concluding that we should have rejected HO, and we should have rejected HO. So I wrote good here. In the lower right corner, you can see the other good decision. This is when we've gone ahead and decided that, no, our sample's characteristics don't exceed the cutoff. So we're going to retain HO and say that there's nothing really very fancy about them. They're just best described by whatever is described by the null hypothesis. And reality is that we should have retained the null hypothesis. So again, we'd be making the proper decision there, retain and retain. But the other two corners that we have on this table, the upper right one that says type 2 error and the other one in the lower left called type 1 error, those are errors that we can make based on our decision making. So let's take the type 1 error first. So here's where the researcher concludes, reject HO. Let's say we have a significant effect. Yet the reality is there really wasn't anything significant. Nothing really was truly happening with that population. In that case, where you've gone ahead and statistically rejected the HO because you thought, well, you found that your characteristics exceeded your cutoff, but you shouldn't have because in nature, in reality, there wasn't anything fancy going on here. That would be known as a type 1 error. And it has a little Greek symbol associated with it called alpha. So alpha is the probability of making a type 1 error. So your chances of making a type 1 error are defined by alpha. Over in the upper right corner, this would be the other kind of error you can make where you've gone ahead and said, oh, I'm not going to reject the HO. I'm going to retain it. I'm going to go ahead and say the null hypothesis is fine. It's probably the best way to account for my data. But in reality, you should have rejected it, that maybe your sample really didn't come from that population. So in that case, you'd be making another kind of error called a type 2 error, and it has a symbol associated with it called beta. So beta is the probability of making a type 2 error. So we can actually estimate the probability of making a type 1 error called alpha, and you can also estimate the probability of making a type 2 error called beta. And you'll notice that I've also had one other way that I've used beta here, and that was to make that correct decision of rejecting HO when I should have rejected the HO. And that good decision there, the probability of doing that is 1 minus beta. So the probability of correctly rejecting when I should reject it is known as 1 minus beta. Let's go ahead and take type 1 error first, the alpha. The probability of rejecting the HO when the HO is true. As I said, this is known as alpha. And it's the same thing as our significance level. That is, whenever we say that we're going to decide whether it's 0.05 or 0.01 or 0.001, when the p-value has to be below a certain criterion, we're actually setting alpha. So when we say p is less than 0.05, we're stating that the type 1 error here is less than 5%. So our chances of making a type 1 error are happening less than 5% of the time. So that's something that we usually decide beforehand, what acceptable level of alpha we're going to have. What about the other type 2 error there, the one that's beta? Well, this probability of retaining the null hypothesis when the null hypothesis is false is what type 2 error is, also known as beta or beta. We know that it's a probability, and it's very much determined by whatever the alpha is. So there's a relationship here between what you've decided alpha is and what beta is going to end up being. So generally, as you decrease your alpha, you make it a smaller number, you're going to be increasing your probability of making a type 2 error. Or the other way to think of it is, generally as you increase your alpha, increase the chances of making a type 1 error, you decrease your beta. So the problem is you can never get rid of one or the other completely. Because if you make one smaller, chances are decreasing one, you're increasing the chances of making the other. And that's how psychologists came up with this convention of picking an alpha of 0.05 or 0.01 because those were based on a compromise of the two types of error. So we have decided on those as conventions because that seems to be the best way of making sure that your beta isn't too high and that your alpha isn't too high. Now, as I said, we also had that one really good decision there, which is reject the null hypothesis when you should have rejected it. That's when you really found a significant effect, and reality is you had a significant effect. So that's something that we like, and it has a special probability associated, 1 minus beta. But there's also a name for this that you've already been introduced in previous weeks. The name for this probability is power. So when I talked about power earlier in the semester, I was talking about this probability that you would correctly reject the HO when the HO was false. So that's the power, is the probability that a researcher will correctly reject the null hypothesis when the null hypothesis is false. So just like any other kind of power that happens in life, we would like to have as much power as possible when we're analyzing our data, because then we'll be able to correctly reject the HO and know that there really is an effect in our study. Let's try to understand power a little bit better by taking a visual look at what power is. So what I've drawn here up at the top is a distribution of sample means for the population when the null hypothesis is rejected. So this is what reality is, that there really is a population up there that has a mu of 200. And down below, we have a distribution of sample means for a population if the null hypothesis were true. And so that's a mu of 100. Okay? Now, for the purposes of power here, to understand this, let's assume that we're using a one-tailed test and our alpha is 0.05. So we're using a 5% alpha, okay? What this is showing you is down the lower right is what you would use to indicate the 5% of the entire sample distribution of sample means that what it would take for you to reject the null hypothesis. So the tail in blue is the 5% of the distribution where above that point you would go ahead and reject the null hypothesis. What I've done though is I've shown you the right above it what the reality is. So if we look up at the above, you can see that you would need to have any sample mean of 201 or above in order to reject the null hypothesis from below. Now, it turns out that we are really grabbing samples from the population that's up above, and it has a mean of 200, that entire population. But as we take out samples from there of whatever our sample size is, and we look at their means, occasionally we're going to get 201 and above. But you can see that we have a lot of means that would come in the red there that wouldn't have a sample mean of 201. They'd be less than 201, right? So anything that's in red up at the top would be a sample mean that we would draw, but we would end up making the inference that we couldn't reject the null hypothesis because it wouldn't exceed our cutoff, even though reality is they really did come from that population up above. So what we can do is estimate what our power is by looking at how much of that curve up at the top is actually going to give us a mean that we could reject when we're testing it against the null hypothesis at the bottom. And that turns out that that probability, the way I've drawn it up above, is 0.45 or 45%. So 1 minus beta up there is 45%. This is the power of our study, okay? So that means that if I draw a sample of 190, and I pull that person out of there, this sample out, and I come up with a mean of 190, that would be a sample mean that would not exceed my cutoff, and I would end up retaining the null hypothesis when I should have really rejected it. So I'd be making a mistake, right? I'd be going ahead and assuming there really wasn't anything going on when there actually was something going on. So I need to increase that power. We want to have as much power as we can so that we don't make that error. So how do we maximize the power in a study? Well, one of the ways that we do this is to increase the effect size. Okay, so one way we can do this is increase the effect size. Another way is to increase the sample size. A third way is to increase alpha. And the fourth way is to use one-tailed tests instead of two-tailed tests. So let me show you how each of those four ways maximizes power. In the first way, I said you can increase your power by getting bigger effect sizes. By getting a bigger effect size, I mean make the difference in the means between the population that's described by the HO and the one that's described by your research hypothesis be as big as possible. So instead of having a mean of 200 up above, I have a mean of 220, and that moves the whole distribution off to the right. And so by having a bigger effect, you can see that down below, I'm still using 201 as my cutoff. That's the part that marks off the top 5% that would allow me to reject the null hypothesis. But that's giving me more means from up above that I could just get by chance that would cause me to reject the HO. So that's one of the ways that I could increase my power, is just by increasing the effect size, making sure I have as big of an effect as possible so that I can have more sample means that would give me, just by chance, something that I could use to reject the null hypothesis. A second way that I could increase the power is by increasing my sample size. Okay? And the reason that would happen is that without even changing the means here, so here I've got the mean of 200 as I originally had for the research hypothesis, and down below I've got the mean for 100. And what you can see is that I'm going ahead and using a bigger sample size this time. And what that's done is by increasing a sample size, it decreases the variability. It makes the spread of my distribution of the means narrower. It's a skinnier distribution. And by making both of them skinnier, it's gone ahead and drawn it so that now there's more in blue up above that overlaps with my cutoff below. So now having a sample of 190 would actually allow me to exceed this cutoff down below, because my cutoff is now lower because my sampling distribution of the means, or my distribution of sample means, is narrower because I have a bigger sample size. Now you have to again think about this, that the distribution of the means is created by taking an infinite number of samples of some given sample size and then plotting the resulting distribution. And as I said earlier in this lecture, by having a bigger sample size, like using 50 or 100, that would make the overall variability of the resulting distribution of the means less. It'd make it a narrower distribution. Even though it's bell-shaped, it's still a narrower spread. And by having a narrower spread, I increase the power and allows me then to possibly reject the HO. A third way that I could increase the power in my testing is by increasing the alpha. So instead of using 0.05 as my cutoff, I could use 0.15 as my cutoff. And so you can see down below, I've now chosen an alpha of 15% instead of an alpha of 0.05. And by going ahead and going from 0.05 to 0.15, I've lowered the cutoff. So anything down below here, you can see there's a much lower cutoff, and that gives me many more means up above that I could get by chance would help me reject the null hypothesis. The fourth way that I can increase power is by using a one-tailed test instead of a two-tailed test. So I've the whole along here been just using an example of one-tailed test, but here's what it would look like for a two-tailed test. If I had a two-tailed test, which is the more common way that we test things, if I use a two-tailed test, you can see that my cutoff is actually quite high now because I've taken that 5% and I've split it in the distribution down below. 0.025 at the top, 0.025 at the bottom. So even though I have just an alpha of 0.05 here, I really only have 0.025 at the top, which gives me a higher cutoff. And then if I look at the distribution up above, that gives me fewer means from the alternative distribution of means that would allow me to reject the null hypothesis. But if I go ahead and put my entire 5% up in one tail, like we have in this example, then you can see that I've lowered the cutoff because having the entire cutoff there now makes more of the means up above possible to reject the null hypothesis. So that's the fourth way to increase the power. Note that it is possible to actually calculate the power. You can actually determine it. It's often, though, very difficult to compute power by hand. So a lot of people just rely on power tables, but there are now websites and programs that you can download where you can type in numbers like your alpha, your sample size, your effect size, and everything, and it will compute the power for you. And so power is now a probability that people can compute and report as part of their study. So you're not going to be asked to do that this semester. We're not going to be calculating power at all, but I want you to understand what power is because, as I mentioned earlier in the semester, it's one of the 4 main pillars that underlie everything that we're talking about this semester. So again, how do we maximize power? We have 4 choices. We could increase the effect size, we could increase the sample size, we could increase the alpha, or we could use one-tailed tests instead of two-tailed tests. Of course, you could use combinations of these things. You could increase the effect size, increase the sample size, and not do anything about increasing alpha or using one-tailed tests. Any of those combinations actually will work to help you increase the power, and we want to maximize power as much as possible. So that lecture now has covered all the main points that you need to know about. There's some other more things that are gone into detail in the text, so be sure you again read the text, try out some problems, try to do a Z test yourself. Try to do this all before you take the quiz so you'll be prepared as you take the quiz online this week. And we'll see you at the workshop.